defect. Crystal defects are imperfection in the crystals or deviation from the ideality. That is, when there is the imperfection, when there is the distortion in the crystal, when there are the impurities or any other kind of the defects, then this is called as imperfect crystal structures or defective crystal structures. So crystal defects are imperfections in the regular geometrical arrangement of atoms in a crystalline solids. These imperfections can be results from the deformation of solids. It can be due to the rapid cooling from the high temperature, or when the high energy radiations like the X-rays or neutrons striking the solids, or it can induce the crystal defects within the crystal. These defects can be located at a single point, or it can be along a line, or it can occupy the whole surface of the solids. So here we will discuss as how these defects influence the mechanical, electrical and the optical behavior of the crystals. So first of all, now we discuss the classification of defects. Here we classify the crystal defects on the basis of their dimensionality. So first of all, we can classify these crystal defects on the basis of dimensionality. These can be the zero-dimensional defects, or these can be the one-dimensional, two-dimensional and three-dimensional. So zero-dimensional defects, these contains point defects, and point defects can further be subdivided into vacancies, impurities, and it can be the Frankel defects or it can be short defects. All these kinds of defects are the point defects. We call these defects as the point defects or zero-dimensional defects because these are related to the points. These are related to the atoms, atomic sites within the crystals. So these are the defects which are related to the different atomic sites within the crystal. So these are called as zero-dimensional or point defects. And one-dimensional defects are called as line defects. That is, these are along the lines. So these line defects includes the dislocation, and like the edge dislocation or screw dislocations. In the coming slides, we will discuss in detail that what are the edge dislocations and what are the screw dislocations. And two-dimensional defects, these defects are also called as the surface defects or interfacial defects. These includes the boundaries like twin boundaries, grain boundaries, stacking force, or it can be the tip boundaries, and later on we will discuss in detail about all these kind of defects. And three-dimensional defects, these defects are also called as the volume defects because these defects occupy the whole volume of crystal structures. So that's why these are called as the three-dimensional or volume defects. These defects includes like dispersant, precipitates, inclusions, or it can be the voids, or it can be the cracks. So first of all, we are going to discuss point defects. Point defects are the defects which are due to the points, which are due to the different atoms on the lattice sides. These point defects includes like vacancies. These defects can be impurities, Frankel defects and Schottky defects. Further, we can subdivide impurities into substitutional impurities and it can be the interstitial impurities. As we know that atom within the solid possesses the vibrational energies, and some of the atoms with enough energies are being able to break the bond and become free, thus creating the kind of point defects. So now we are going to discuss all these defects, point defects, one by one. So dear students, first of all we are going to discuss vacancies. Vacancies are simplest kind of point defects, and we can say that these are the vacancies are actually the vacant lattice sites which are normally occupied. So these are the vacant lattice sites from which an atom is missing. So here in this figure you can see the vacancies. So once these are occupied, when atom leave this sites, these become vacancies. So vacancies are the vacant lattice sites which normally occupied by the atoms. Number of vacancies for a given quantity of materials depends on, and it increases with the temperature according to Nv is equal to N exponential of Qv divided by kT. Here Nv is the equilibrium number of vacancies which is present within the crystalline materials, and N is the total number of atomic sites, and Qv is the heat required to create the vacancies, and K is the Boltzmann constants. Here we can see in this relation that equilibrium number of vacancies is related with the temperature. That is, when we increase the temperature of the material, it increases the number of vacancies. That is, as we notice, all atoms have the vibrational kinetic energy. When we increase the temperature, these atoms vibrate with greater kinetic energies, and some of atoms get enough energies that it can break the bonding with the other atom and it becomes free. So when it becomes free, it moves from its lattice sites and leaving behind vacancies. So we can say that as we increase the temperature, it increases the number of vacancies. So for most of the metals, the fraction of vacancies, that is Nv divided by N. Here I have already told you that Nv is the equilibrium number of vacancies and N is the total number of atomic size. So just below the melting temperature, this is on the order of 10 to the raised power minus 4. That is, one lattice sites out of 10,000 will be the empty. That is, if we have the 10,000 atomic size, the one lattice sites out of 10,000 will be the empty just below the melting point, and this is the case for the most of the metals. So we can say that the number of vacancies are relative with the, and it also depends on the temperature. When we increase the temperature, it increases the number of vacancies, and that is the more and more atoms get enough kinetic energy and become free, thus leaving the lattice sites and thus creating the vacancies. So then now we go to the next point defects, that is called as impurities. So now we will discuss the point defects, impurities. So all pure metals consisting of only one type of atom, that is it is not possible. Impurity or foreign atom will always be present, and some will exist as crystalline point defects. So we can say that if it is not possible to synthesize the highly pure materials. In fact, even with a relatively sophisticated technique, it is difficult to refine any metal to a purity in the excess of 99.999%. At this level, on the order of 10 to the raised power 22 to 10 to the raised power 23 impurity atom will be present in the 1 cubic meter of the material. So, the most familiar metal are not highly pure, rather they are lies. Sometimes we intentionally add the impurity atom to induce the specific desired properties in the material. Like we can say that, for example, the sterling silver, which is the 92% silver and 8% copper, at the ambient conditions, the pure silver is highly corrosion resistant, but at the same time it is highly soft, that is very soft. So to make it mechanically stronger, we add some copper. So the copper enhances its mechanical strength without disturbing its ability to corrosion resistivity. Or in the same way, similarly, when we add carbon to the iron, we make a steel, which is the most strongest kind of the material. So when we add the copper to the nickel, it also we can make the thermocouple wire, and like germanium to silicon, then we can make the thermoelectric material. So we can say that impurities are not always cannot be implies as a bad thing. Sometimes we intentionally add the impurities to the material to induce the desired characteristic. So lies in which we add the impurity intentionally to impart the specific characteristic to the metals. So we intentionally make the alloys by adding some kind of impurities. So we can divide the impurities into two types. These can be the substitutional, or these can be the interstitial impurities. So here we are going to discuss both these kind of impurities. Before going to discuss the interstitial and substitutional impurities, it is very important to discuss another terminology, which is solid solution. The addition of impurity atom into the metal will result in the formation of solid solution. So the solid solution forms when a solute atom are added into the solvent material. Here the solute atoms means that impurity atom, when it is added into the host material, the crystal structure is maintained and new other structures are formed. That is, there will be the no new phase of the material, that is crystal structure will be maintained. So here we can make an analogy of the solid solution with the liquid solution. When we add the two liquids which are soluble to each other, for example water and alcohol, both intermixed and compositionally homogeneous in the same, make a homogeneous kind of the solution. So in the same way, the solid solution are also homogeneous and impurity atoms are randomly dispersed within the solid. So the impurity atoms forms the two types of the defects when impurity atoms goes into the host materials. These are the interstitial defects and substitutional defects. So here we can discuss first interstitial defects. Here you can see that when impurity atoms goes into the interstitial sites, which are normally void or vacant spaces within the crystal, that is, usually these are not occupied. The size of these interstitial sites are always less than the occupied site size. So when impurity atoms of relatively large size goes into these interstitial sites, it creates a strain in the crystal. So it can distort the crystal structure. Consequently, the formation of this type of the defects is not highly probable, and it exists only in a very small concentration. For the substitutional type, here you can see that these are the substitutional impurity atoms. For the substitutional types, the solute or impurity atom replace the host atoms. Here you can see in this figures that impurity atom here, this replacing the or substituting the host materials. So there are several important features which determine the degree to which the impurity atom can be added to the solvent. So the first important here factor is the atomic size factor. So when the difference in the atomic radii, when the difference in the atomic radii is in the range of plus minus 15%, that is, then the solute atom can easily be dissolved into the solvent. Otherwise, the solute atom will create a substantial lattice distortion and the new phase will form. And the second important feature is the crystal structure. So for good solubility, the solid solubility, the crystal structure for both the metals type must be the same. So another important feature is the value of electronegativity. The more electropositive one element and more electronegative the other, so the greater will be the solubility. So they instead of, we can say that when one is the more electropositive and other is the more electronegative, then there will be greater probability that they can make an intermetallic compound instead of substitutional solid solution. And another important factor is the valency. The valence states are very important. So it means that metal will have more of the tendency to dissolve to one another metal of higher valency than one of lower valency. So if we want to add the impurity atom into the solvent, so we should add the impurity atom of higher valency. The impurity atom should have the higher valency as compared to the solvent, then it can be easily dissolvable in the solvent. Now we are going to discuss the point defects in the case of ceramic materials. In ceramic materials, we know that the ceramic exists in the form of ions, like there are the cations and anions. cations are of smaller size and anions are of larger size. Cations are positively charged and anions are negatively charged. So the impurity atom can form the solid solutions in ceramic material as they can form in the case of metal. Here the solid solution of both substitutional and interstitial types are possible, as we have already discussed in the case of metals. So for example, for an interstitial kind of the solution, the ionic radius of impurity must be relatively small in comparison to the anions. Since there are both anions and cations, so the substitutional impurity atom will substitute for those host ions to which it is more similar in the electrical sense. For example, left we have the sodium chloride solution, in which the sodium is the positively charged and calcium is the negatively charged. So chlorine is the negatively charged. So in order to replace the sodium, we need the impurity atom which should be the positively charged, and in that should have the same ionic radii like sodium. For example, the calcium. Calcium can easily replace the sodium because both are positively charged, and chlorine can be substituted by the oxygen atom because both are negatively charged. So to achieve the good solubility of substituting impurity items, for substituting the impurity atom, the ionic size and charges must be very nearly same. So these two are the important factor in the case of ceramics. The ionic size and charge of both the solute and solvent must be very same. For an impurity ions having different charge from the host ions which we want to substitute, so the crystal will compensate this charge difference. So in order to compensate this charge distance and to maintain the electrical neutrality, so this will be accomplished by the formation of lattice defects. So defects will be induced when crystal will try to maintain ceramic crystal will try to maintain its electrical neutrality. So here you need to understand the electrical neutrality. Actually, electrical neutrality is the state that exists when there are equal number of positive and negative charges. Like in the case of sodium chloride, there are the equal number of chlorine and sodium. So in the case of ceramics, when defects are induced in the ceramics, the defects always occurs in the form of pair. So one such a type of defects is a Frankel defects. So Frankel defects, which these defects are always occur in the form of pairs. For example, here you can see in this figure, that is this white color, which are smaller in size, these are the cations. When there is a cation vacancy, then there is the cation interstitial, that is cation leaving its place and is coming to the interstitial side. So these defects occurs in the pairs. When there is a cation vacancy, then there is cation interstitial. Why they are in the pairs? These are in the pairs in order to maintain its electrical neutrality. That is, we can say that it is formed that when cation leaving its normal position and it moving into the interstitial sites. So there is no charge and there is no change in the charge because cation which leaving this occupied sites and moving into the interstitial site, it maintains the charge of this crystal. So the important thing here to notice is that there should be the electrical charge neutrality within the ceramic crystal. So when cation leave its position, it's move into the interstitial sites. So at a time there are two types of the defects: cation vacancy and cation interstitials. So another here you can see that this is the cation vacancy and this one atom cation occupying the interstitial site. So another this type of the defects are called as Schottky defects. Here the cation we can see that these are the anions. The yellow colors are representing the anions. These are larger in size, and the cations, green color is representing the anions. So the Schottky defects are also occur in the form of pair. When there is anion vacancies, then there is anion interstitials. Here you can see in this figure that this is the place of anions, and this is here the anion is missing, that is here is anion vacancy. So here you can see that in the same way there is the this is the place of cation. The cation is also missing, so there is the cation vacancy. So when there is anion vacancy, then there should be the there should be the when there is anion vacancy, there is the cation vacancies. So these defects occur in the form of pairs. Why there is the when there is a cation vacancy, when there is the anion vacancy, it means that defect is created by removing the one cation and anion from the interior of crystal and replacing both them at an external surface. So both cation and anion having the same charge. So since for every anion vacancy there exists a cation vacancies, this means that when we from here from the interior of crystal, when we remove the anion and place it on the external surface, then it means that it will disturb the electrical charge neutrality of this crystal. In order to maintain the electrical charge neutrality, then one cation will move to the outer surface to maintain this charge neutrality. So these defects always occur in the pair. When there is an anion vacancy, then there is cation vacancy. So these are the kind of point defects which occur in the case of ceramics. Now here we are going to discuss the one-dimensional defects, which are also called as the line defects. The dislocations are one-dimensional defects around which the line of atom or plane of atom is misaligned. That is, there will be an extra portion of a plane of atoms, or there will be the half plane, which is also called as the edge dislocation. That is, the edge of the half plane is terminated within the crystals. So here this is called as edge dislocations. Here you can see in this figure that when enough force is applied from one side of the crystals, that is, this crystal structures, when we apply the force, the extra plane of the atom passes through the planes of atom, thus making and joining the bonds until it reaches the boundary. Here you can see that this extra half plane of the atoms, it starts from here when we apply stress, and it's moved throughout the crystal, thus making and joining the bonds until it reaches here. This kind of the defects are called as edge dislocations. There are some important terminologies which are related to this edge dislocation. These important terms are the line of dislocations. The line of dislocations, this is the called as the line along which the distortion occurs. That is, and another important parameter is called as the Berger vector. The Berger vector is the vector which tells us the magnitude and the direction of this dislocation, that is, along which this dislocation is going to take place. So here in this figure we can see that this is the extra half plane, or here is the edge dislocation in this crystal structure. The line of, we can specify here the line of dislocation. Line of dislocation lies into the plane of the page. That is, here you can see that line of dislocation will be along this direction, that is into the plane of the page. That is along the line. This is the line along which this crystal plane is terminated. Within the region around the dislocation line, there is some localized distortion within the crystal. The atomic atoms above these dislocations lines, here you can see that these are going to squeeze together. Atomic planes are going to squeeze together, and those which are below, these are pulled apart. That is, we can see that as we go away from this dislocation at very far distance, we see that crystal looks very perfect. So this is the kind of localized kind of dislocations. So here we can see that when we see this crystal structure from here, that is from these planes, when we look these bottom planes and ignoring these above planes, we see that the crystal structures looks very perfect. There is no edge dislocation in these bottom plane. In the same way, when we look at the crystal structure above these dislocations, that is, when we see the crystal structure from these planes, here we see that there is no edge dislocation. That is, crystal looks exactly perfect. So it means that as we go away from this dislocation lines, the crystal goes very perfect. So this kind of dislocation is the very localized, is along the line of dislocation. So another terminology which we need to discuss here is the Berger vector. Berger vector, we can say that it's a small lattice translation. Here it is a small vector which tells us the magnitude and the direction of this lattice distortion due to this dislocation. We can draw it, we can denote it by a small letter b, and it can be drawn from this plane to this plane. Either it can be from here to here. As I have already told in the previous figure that when we apply a stress from one direction, then this dislocation move along, or this extra half plane move along the whole crystal, thus making and joining the bonds. That is, it translates from here to here, from here to here, from here to here until it resets the boundary. It means that Berger vector is a small lattice translation along the line of distortion. So it can be drawn between these two planes from here to here in these planes. So another important thing here about the edge dislocation is that here the Berger vector and the line of dislocation both are perpendicular to each other. That is, line of dislocation lies into the plane of the page, while the Berger vector is from here to here. That is, both are perpendicular to each other for the case of edge dislocation. Another type of dislocation called as screw dislocations. These may be thought of as being formed by a shear stress that is applied to produce a distortion. So the Berger vector here and the line of dislocations are parallel to each other. We can also say that the Berger vector is the slip direction parallel to the line of dislocation. So here in this figure you can see that this is in this figure the line of dislocations. Okay, I am going to draw here the line of dislocations. So the dislocation line will be along, it will be along this direction, this one. Okay, along this direction. This will be the line of dislocation. So okay, we can say that the line of dislocation which is along this plane and the Berger vector which is the slip directions, these both are parallel to each other. The upper front region of this crystal is shifted to the left sides with respect to the right. That is, when it shifted, when we apply the shear stress along this direction, this upper portion is shifted to the left side with respect to this bottom region. So the atomic distortion associated with this screw dislocation is also a linear, that is along the line of dislocation. That is, it's not along the whole crystal, but it is the localized stress, it is localized type of the distortion that is along this direction. As crystal, that is this plane, moved one atomic distance apart, so the Berger vector will be along this direction. That is, in this case both are parallel to each other. The screw dislocations, we call it a screw dislocation, is derived its name from the spiral or helical path or ramp that is traced around the dislocation line by the atomic planes of atom. So here we can say that if we start from here, that is, if we draw a line from here along this path from here to here, then we comes here, that is to the bottom planes. This line is not going to join this upper plane, either it's go to the bottom plane. That's why it is called as screw dislocations. So now how the screw dislocations move. The motion of screw dislocation is also a result of shear stress, but the defect lines movement here is perpendicular to the direction of stress and the atom displacement rather than parallel. as in the case of edge dislocation. When the shear stress is applied to one side, the atom moved to their new position. That is, when we apply the distortion stress from here, that is, atoms are going to move to the other new position in the lattice and have and try to re-establish their metallic bond. That is, they are going to making and breaking the bond. When we apply stress from here, it's moved to other directions and occupy a new space within the crystal, thus creating and making and the breaking the bond. So some atomic planes are in the process of moving. It can be seen only the portion of the bonds are broken at any given time. That is, not all the bond is going to break all the bond at the same time. That is, when it moves from here to here, that is again it makes the bond and it's breaking the bond and moving forward to the other boundaries. So this is the kind of this is the movement of the screw dislocation which can be observed in the case of crystals.